The annular end seal system, an innovative solution for annular pipe sealing. Stevic International in partnership with Southern Gas Networks. Presented to you by Nicole Fever. Southern Gas Networks, SGN, approached Stevic International, SVI, to design and develop a method of permanently sealing the open annular space between Tier 1 metallic pipe and inserted polyethylene pipe. As you can see with the help of the red arrows, the annular space between the polyethylene pipe and the metallic pipe in Figure 1. The first question you may ask is, why seal the ends? The seal is required to prevent the ingress of water and backfill material, which can lead to road surface slumping. The seal will also prevent the potential tracking of gas through the old annular space, which can lead to expensive and time-consuming leak investigations. The scope for this project was to design and develop a sealing system which could be used by SGN main-laying operatives after a small amount of training. Initially, the system would be designed to work in conjunction with SGN's I-Core excavation system, but not limited to this. The system should be able to function properly in cleanly cut cast iron pipes and pipes with rigid or broken ends. Figure 2 is an I-Core excavation with the use of a long-handled tool. Figure 3 is a standard gas replacement. The final product will fill the annular spaces of the following sizes: 75 mm polyethylene pipe within 4-inch metallic pipe, 125 and 6, 140 and 8, and 180 and 8. Figure 4A shows our baseline product. Foam Pack is a sealant already approved within the gas industry. This product is a sealed unit with a disposable spine that separates two chemicals. Once the spine is removed and the chemicals are mixed, it is then inserted into a cartridge where it bursts during injection. The mixture will expand into a closed cell foam that meets GIS LC14 2009 specifications for a gap annular sealant. During the baseline tests, I tested the tensile strength of the outer seals on the Foam Pack sachet and replicated this on our sonic weld machine. Through further testing, I found a suitable setting that could create a burst seal. By using the burst seal, we are replacing the one-use plastic, aka the spine, on the current Foam Pack. As you can see in Figure 4B, we have the outer packaging, Part A resin, the temperature gauge, the two-part spine, the protective sleeving, and within, Part B hardener. Figure 5 and 6 are the sonic weld machine I mentioned earlier, and Figure 7 was the testing of the burst seal. The first round of testing that I carried out did not use any chemicals. Instead, I used water. I added food coloring into one side and then proceeded to add pressure to one side of the sachet and eventually force the middle burst seal to open. And with the help of the red coloring, I could check for imperfections and holes that the sonic weld machine might have left. On the screen now will be a demonstration of that experiment. For manufacture and production in the future, we already have started discussions with sachet manufacturers. Using the weld settings, I then started volume testing to decide the quantities needed to successfully seal each individual annular space. As there is a fine line between what will fit in the very small annular space and the quantity of foam needed to create a sufficient seal, a great deal of testing and retesting was needed to arrive at the optimum solution. Once SGN representatives witnessed the designs most suitable for each pipe size, field trials were discussed. While the field trial locations and communications were dealt with on SGN's end, I continued testing and perfecting the designs. As you can see it on screen now, figure 8 to 13. Product requirements that needed to be taken into consideration at this stage. The sachet needed to fit into the annular space, not being too bulky or oversized. The sachet must hold 2 chemicals of a specific volume separately until needed. Once the chemicals are fixed, the exit point opens because of the pressure the foam creates as it expands. Through testing, I found a plethora of information that later influenced the final design, such as the rectangular shape made the central burst seal more difficult to open because of an increase of surface area. The shorter the burst line, the easier it is to burst. Having the same shape on both sides of the sachet makes it easier to mix. Final testing and design. Once I have a better understanding of the design's influence on how the foam behaves, we can introduce a way to adapt this product to an I-Core product and still make it usable for standard mains replacement. There are hundreds of methods we could use, including, but not limited to, mechanical mechanisms, hinges, loops and wire. As a collaborative development team, we decided that the more we can simplify this product, the better. The final decision was to put channels either side of this annular sealing sachet that can either be biodegradable wood dowels for structural support while you insert the sachet by hand, or remove the dowels and you can insert a metal prong tool that can be easily attached to the I-Core long reach system. Figure 15 is a photo of myself demonstrating an early design for the SGN representatives. Figure 16, I am demonstrating on site the use of an annular sealing bag for the first time. Figure 17 was the very first burst seal tested with water. And figure 18 is the final design of an annular sealing sachet with wooden dowels. You are now going to watch a short clip of how the annular sealing sachet is used. Squeezing one end, you can open the burst seal in the middle of the sachet. You then mix the 2 chemicals until they are a consistent color. In this experiment, I am going to use a long reach tool and therefore insert the sachet using 2 metal prongs. I will then lower the sachet into my artificial excavation and insert the sachet into the annular space. The field trial stage. The manufacture of handmade annular end seal sachets included manually weighing out each chemical, filling both sides of the sachet, and sealing the ends. After I wipe them down, I carry out a visual inspection for leaks or imperfections. If they pass the visual inspection stage, then the sachets are ready for packaging. I then box the sachets, including correct labels, information, instructions, and PPE. This is a very time-consuming manufacture process that I carry out for each field trial. And if the field trials were given at a very short notice, I would then have to put in hours of overtime to get them ready. I personally supported site with an SGN representative multiple times. This included traveling to Scotland to demonstrate and train 2 separate main-laying teams. I then supported them as they carried out field trials, collecting images and feedback. Each size is trialed at least 12 times. 6 inserted by hand, and 6 inserted using a long reach tool. This was carried out over multiple sites and days over the time span of approximately 6 months. All feedback that had been witnessed, written, or verbally given had been incredibly positive. The product can be mixed and inserted within 1 minute, and the annular seal will be established, even without the main layers having to be there. We advise a 30-minute reaction, expansion, and cure time before a visual inspection, and then the trench can be filled as per usual practice. Figure 19, I am demonstrating the burst pouch on site for the first time to one of the main laying teams. Figure 20 and 23 are main layers inserting an annular sealing bag by hand. Figure 21 is a main layer inserting the sachet onto a long-handled tool. Figure 22 shows the sachet being inserted using the long-handled tool. And Figure 24 is a visual inspection of the seal after the foam has expanded in the annular space. Thank you for listening. Please send any questions to nicole.fever@stevevic.com.